So, good morning, all of you. In the last lecture, in lecture 18, we were doing basically we completed the Gram-Schmidt orthonormalization process, and whatever background from linear algebra required, we just did it on the fly. It means whatever we wanted, we just presented those concepts in the context of Gram-Schmidt procedure. Okay, assuming that we have sufficient background in the course of linear algebra. So we then discuss orthogonality, orthonormality, dividing by the norm, projection, and everything we did. And we found out that if at all given capital M functions, maybe over a time interval of 0 to t, you can find out capital N number of functions which are orthogonal to each other and they have a unit norm. It means that those capital N functions will form an orthonormal set. Okay, and we saw that capital N has to be less than equal to capital M. This is what we basically, I think we didn't prove it because we know that the dimension, from the concept of dimension, we can say that the number of elements in the set cannot exceed the, so it will exceed or will be equal to the number of dimensions of that set. This is from the linear algebra. So we said that n, capital N would be less than equal to capital M, and we saw two cases when capital N would be strictly less than M and capital N would be equal to M. So we saw that if S1, S2 and SMT, if they are linearly independent, then capital N would be equal to capital M. And if at all they are not linearly independent, then definitely capital N would be less than capital M and functions are 0 for I greater than N. It means, let us say, let us say you are repeating this process, okay? You are doing the Gram-Schmidt process, and after the nth iteration, in capital N iteration, all of your functions would come out to be 0. That is the meaning of this, okay? So it means that is a signal that you have to stop at this point. So either you have to stop when n is equal to m, which will be the case, which is case 1, or you may land up with a case where you will find that for I greater than n, you are getting all of gi's as 0, then you can stop. Okay, it means you have found out the set in whose terms all of the capital M functions can be written. So this is what we saw. Then we did one example, and we closed our lecture at this point. And I said that in the next lecture we will be doing random processes. Now this, with the introduction of the random process, now we will enter into the communication systems or study of communication systems in a noise limited environment. Okay, so study of communication systems in a noise limited means that additive noise we will be considering. Additive. Okay, so first we will do this. Now, in order to do this, we require the background of random processes. First of all, noise limited mostly from the random motion of electrons in the circuitry at the receiver. Okay. So mostly this AWGN is from this. This is a sort of a additive noise. Okay. Now, in order to build a base, let us see one thing. Suppose you have a transmitter receiver pair connected through a wire. Okay, so you have a box and you have a wire connection. This is the receiver, and daily at 9 a.m. you transmit the same file, you transmit a file for 15 minutes, okay? And you check the RX output. So what you will see is generally that daily at 9 a.m., suppose from 9 a.m., this happens from 9 a.m. to 9:15 a.m. And at the receiver, you see the receiver output. So suppose this is the output which you are getting. Then this is day 1. Then this is suppose day 2. Same time, but the output is again somewhat different. Okay, and this continues. Suppose day n. Now what you do is you subtract what you transmitted. That is because you are the same person, you know what file you have transmitted. So after transmitting the file or the signal, you observe that you get, let us say, n different waveforms. Okay. Suppose you get n different waveforms which represent the noise in the system. Why? Because we have to account for it. When you have subtracted, ideally, if at all there is no noise in the system, so first of all, in order to not complicate our case, we have not assumed wireless communication. We are simply assuming that there is a straight wire, and at the receiver, you are observing whatever you have transmitted, and because you know what you have transmitted, you subtract the transmitted signal at the receiver. So you will get waveforms. Ideally, you should say that there should be zero signal. You should get only a zero level or a signal which is a very low in magnitude. But this is not the case. This is what you observe. Now this is mostly because of the circuitry at the receiver. This has a basically constant motion of electrons, and this generates this. Our purpose is not to go into this phenomenon. Okay, that why does this noise why the noise is present at the receiver. We assume that this is there, and as communication system engineers or designers, we have to somewhat do away with it. So first of all, let us study structure. किस तरीके का noise है? That is very important for us to understand that what sort of noise is this. So we get n different waveforms which represent the noise in the system. Now this n can be very large, very small, n can be very large, very small. So this leads to several possibilities. Now what to do? See, how do you study the system? So what can we say is that for the duration of 15 minutes, let us say this is my 0 time and this is my 15th minute in time, or 15th minute, it is 0 minute. And on this axis, suppose I say that for every possible time, there is a random variable. Okay. For each of the time instant, there is a random variable. Okay. Now what does this mean? Suppose let us assume that अभी हम लोग एक कुछ discrete levels पे study करते हैं. Suppose this is the first time, or you can say just the time ahead of 0 minutes. So you assume that there is a random variable which assumes a value at this point. Suppose today it assumes this value. Then next time there is another random variable which assumes a different value. Then third, it assumes different value. Then this is different. It means, let us say we have divided the axis into suppose 10 points. So 10 random variables are there, and each random variable assumes some value. So you get one waveform. And maybe others, whatever the value they achieve, we get one waveform. Now next day, tomorrow, let us say today we have done this. Next day, again this random variable will take a different value because this is a random variable. Suppose it takes this value. The next random variable takes a different value. This takes, let us say, a different value. Then this takes a different value, and this way you get this. So maybe you get some different sort of waveform. And this way you will see that you get n sample waveforms. N sample waveforms can be seen, okay, or generated, whatever you call slash generate. Okay. So this way, if we put this sort of a structure over these waveforms, we can study them well. Okay, and this is what is a random processes. It is a sequence of random variables. Okay, so what is this? This is basically nothing but it is a sequence of random variables. So if we model such waveforms by sequence of random variables, we can study them well. And unless we study them, we cannot basically design algorithms or schemes at the receiver for extracting our signal without much of the noise. Okay, so you can clearly see that there is noise present in the system, and this will definitely corrupt the data. So you need to study this so as to get or to design a better receiver. Okay. So this sequence of random, let us say you have 4 random variables, x1, x2, x3 and x4. Each of them uniformly distributed somehow the screen is hanged. So each of them uniformly distributed. Okay. Now you say that you have 4 time instants and you are collecting vectors. So this is time instant 1. So it means, let us say you collect a vector. So x1 take uniformly distributed in, let us say 0, 1. Okay, suppose it takes a value 1 by 2, then another value takes 1 by 4. Suppose this takes a value 1. Okay. Then at the second time instant, suppose I collect another vector. This might take any value, that is 1 by 6, this takes 1 by 5, 1 by 7, this takes value 0. Okay, then you create the third vector. Okay, suppose this is 1, then this is 1 by 7, 1 by 5, then this is 1 by 3. And this leads to several possibilities. Okay, so what we have done is that we have created a sequence of random variables, indexed random variables in the x1, x2, x3, x4, and we are running experiments and we are collecting vectors. So this is nothing but a stochastic process or a random process. Okay, so random variable assumes a particular value, but the random process would be a, you can say, suppose in the case of discrete thing, it is a, you can say, a vector. In the case of a continuous time, it would be a waveform. So that is pretty much the difference between random variable and random process. I am defining it. Okay. With this background, let me go ahead and define things. So first of all, let me write down a few things. This I have taken, this whatever I am typing or writing, you can say, I have taken it from Madhav's book. This is very good and presented well there. So for initial part, we will be taking from that book, and then we will be referring Couch's book. And they have given these things quite well. And for your general understanding also, please go through these books. You will really learn a lot for your lifetime. Okay. So noise cannot be modeled as a deterministic waveform. Okay. So whatever background we have built above, that will help you comprehend whatever I am writing in deterministic waveform. That is, we do not know what noise waveform we will observe at any given point of time. Okay, that is quite clear. You can see from here that if at all we are running the experiment or during the same time slot every day, different waveforms we are observing. And even if I am sitting at this point, suppose I am sitting at this point, it is difficult for me to comment that what will be the value at the next point. It means it cannot be a deterministic waveform. You cannot just represent it through some function of time. It is a sine, cos, or whatever function you can define. So that is what is the problem which led to putting a structure of a random process for the noise. Okay, because the noise is not deterministic. You cannot tell even at time instant, let us say 1 second, that what will be the noise value at time equal to 2 seconds. Okay. Second important thing. So why do we study random processes, or what is the problem associated with few things which forces us to include random processes in the study of digital communication systems? Next is the information bearing signal. Now you can relate information bearing signal. Signals such as speech, audio and video are best modeled. This is important to realize, are best modeled as being randomly chosen, as being randomly chosen from a vast ensemble or ensemble, whatever you call, of possibilities. Okay, now you can clearly see. Let us discuss this. See, if at all you are told that you have to design a transmitter for speech or audio and video, let us say you have to design a transmitter for maybe your camera of your mobile. It means your camera will record photos also, it will record videos also. Okay, but the issue is that there are several such scenes over which your mobile can go. It means you can record anything. And if at all you need to design a communication system for communicating that, and you want to study it, you have to assume that the information bearing signal will be chosen from a lot of possibilities. Okay, that is the way to study it. See, my video file can be a video file of the mountains, can be a video file of the city, can be a video file of your home, can be any sort of movie. It means there are several possibilities. So if at all we need to study systems which transmit video and receive video, the best way for us is to model video as some signal which is randomly chosen from a vast ensemble of possibilities. For example, we can now say that if we create such all possible waveforms, let us say if we create all possible noise waveforms, then we can say at the receiver that we are observing one of the possible noise waveforms selected randomly from this set of all possible waveforms. Okay, so that is what we are doing or we do. If there is a sequence of random variables, we can generate all of the possibility. Let us say x1, x2, x1 bar, x2 bar, x3 bar. We generate, let us say, x10,000 bar. That is all the possibilities suppose we generate. And now we observe one of the instance. Suppose now I say I observe 1 by 5, 1 by 7, 1 by 3, and 1 by 2. So you can say that this belongs to this bigger set, and this is chosen randomly. Okay, from this. This is important to say. Means there's, because this is appearing randomly. If I am just running the experiment and I'm getting something, because each of them is a random variable, this whole thing also becomes a random variable. Okay, so but the best way to model it is that we have chosen this from all possible possibilities randomly. Okay, we will see this. I think at this point you can just take it as it is, but we are developing the theory, so you will understand. Okay, so bit streams. This is also important, that bit streams being transmitted. Bit streams being transmitted in a digital communication system. In a digital communication system can be thought as being randomly chosen from a large number of possible bit streams. Number of possible bit streams. So that is also a way to model it. Let us say you studied PCM system. Okay, so you said that if you are assuming an 8-bit, suppose you are assuming 8-bit code words. Okay, or you are assuming or you are assigning a 8-bit code word to every quantization level, and I say that I am now observing this whole you can say bit sequence for 10 seconds. So over 10 seconds there are several possibilities of the bit streams. So given any 10-second bit stream, you can say that that has been chosen randomly from all possible 10-second bit streams. So if you model it that way, it takes you to the theory of random processes. And the theory of random processes is quite well known, quite well studied. You have several results in that theory. So that theory, if we pick up, or if we assume our bit streams, information bearing signals chosen this way, then we can definitely apply that theory to the study of communication systems. Okay. So that is the beauty that we have just linked whatever happens in our systems to a well-developed theory in mathematics, and this give us very good results as well. We designed our systems assuming that they are random processes, and our designs were quite well. Okay, you will see that the receiver design indeed is very well in most of the scenarios, that you can counter noise effectively. Okay. Okay, so now we will formally say a few things. So random processes is a technical term used for signals that are randomly chosen from an ensemble or collection of possible signals. Okay. So there are two things which are really important to know at this point. These two things they are functions of time, most of the cases. These are functions of time in most cases. Okay, means there are other cases as well where this parameter can be maybe coordinates as well. Other cases, let me write down other cases. Instead of time, insert time, or let me take example of other case. That will be a better way to write it, because for us to study this, we must know that ऐसा नहीं है कि random processes will always be a function of time. No, they can be function of coordinates as well. Example for other case. Position of a particle. Okay, that will be a x comma y comma z. Okay, so it says that let us say there is a particle which changes position x y z, there is a position. So based on that position, it assumes a different value. Let us say if I am at this point. Okay, so at this point, let us say my energy is 2 volts. Suppose my energy is, you can say 2, and if I go to this point, then suppose my energy is 4. Okay, and then I come at this point, my energy is again 3. So it means something is there which is changing as I am changing positions. Okay, so in our case, as time is changing, the value is changing. Here, as position is changing, the value, whatever value we observe, is changing. So there is a possibility, or there are cases in which this time can be replaced by a different parameter as well. Okay, but in our case, it would be time mostly in communication systems. Okay, and second important point is, draw this. Second one, before conducting the experiment, this is important. Before conducting the experiment, it is not possible. It is not possible to exactly define the waveform that will be observed in the future. Now there is a point of contention. You can say that when we have collected all possible waveforms, okay, and if I say that this waveform I am observing, so I know what this waveform is. It means if I am at this point, I can definitely say that what will be the next point, because I know what waveform we have selected from this ensemble. No, but the point here is that this ensemble would be rich enough. Okay, it means it will have so many possibilities that at sitting at one point, you cannot say that the next point what point I will be observing. Okay, we will see it. We will be developing the theory. So for the time being, let us assume this is what happens. Okay. So now we will start with the definition of the random process. So up to this we have taken from Upamanyu Madhav's book. This was well presented there. Okay. Now we are going to Couch's book. So definition is, the definition. So a real random process, you can say. So for random processes, we will be defining as RP. Okay. So you can say a real random process means a random process which takes real values, or real random process, or stochastic process, that is also called as stochastic process, is an indexed set of real functions of some parameter. Usually time. That has certain statistical properties. Okay, that has certain statistical properties. Okay. Example is, we have seen examples above, but I am just writing it. Voltage waveforms that might be emitted from a noise source. Okay, that is what example I gave you. So these are the waveforms. You can say they are emitted by a noise source. Why? Because at the receiver we have subtracted what we transmitted, so the remaining waveforms are noise waveforms. Okay. So if at all there is a noise source, noise source means that some source which is emitting the possible waveforms that mimic noise. So that would be a sort of a random process, okay, a real random process, because we are assuming right now real functions. For example, let us see this. So this is what the figure given by the author, and now you can see. So this is a random noise source and some sample functions on the random noise process. Sample function means one of the possibilities of this random process. So you know that it will be a function of time. So that is so E for a particular time. So you can observe that. Let us say at T1. So at T1, if I am running this noise source daily, suppose I am running this noise source from 9 to 9:15 a.m. daily. So at 9 a.m. daily, I can observe different values. Okay. So suppose today I observed this, next day I observed this, next day I observed this, next day I observed this. So you can say that over multiple days, you have several different possible values at a particular time. Okay, and this happens for all time. Now, if you collect all these things, then you land up with all possible waveforms, and then that is what we call as an ensemble. Okay, it means कि अपने ensemble create किया. So this is what the basic diagram is. Okay. So in general, now we will go for the definition that how do you define a random process. So in general, V of t comma ei denotes the waveform, that is obtained when the event ei of the sample space occurs. Okay. So what essentially we are doing is, see, let us say this y is a function of two variables. It is t comma e. Now t gives us the time variation, okay, and e gives us the randomness right now. Okay? It says that let us say if we are looking at t1, then e is varying e1, e2, e3, e4. Okay, and if we are looking at a particular e, then time is varying. So with time variation, you have different possible values. And with time fixed, again you have different possible values. Okay, so that is the way to basically model such, you can say, sources or such phenomena. Okay, or such phenomena. So V of V of t comma ei is said to be a sample function. Is said to be a sample function. To the sample function of the sample space. Of this sample space. Okay. The set of all possible sample functions. The set of all possible sample functions which we denote like this. Is called the ensemble. Is called, means I will vary. Okay, here I and t both vary. Is called the ensemble and defines the random process V of t that describes the noise source. Okay. For the sake of completion, let me write C. I think the figure was 6.1. Now let me write the important thing, that is the events, let us say the events E of I are mapped into a set of time functions. this collection of functions is the random process V of t. Okay. So I will give you maybe 2 minutes to just read this, whatever I have written, and then we will continue. Okay. So we'll start at 9.6 or 9.7. Just go through it and try to take a feel what we are essentially saying. Yes, so with whatever we have written, we can see that what is the difference between random variable and random process. So random variable maps events into constants. Okay? Values you can say. So I am assuming that you know the concept of sample space. Okay. This is you must have studied in your probability course the concept of sample space. If you don't remember, just go back to the book by Ross and you can just know that in order to define a probability, we need a sample space, and you can say that you have some sample space. Maybe let us say this is some sample space S, and there are, you can say, the values in S, and then events are collection of those values. Okay. So random variable, what it takes collection of those values and assigns them a constant or a value. Okay. And what will random process do? So random process maps events into functions of the parameter t. Okay. So with this, I think it should be very clear that how do you really distinguish between random variable and a random process. Okay. Means this will let you understand this. Okay. Although there are several pending things to know about them. Okay. And it's really confusing at the moment. But as we move ahead, I hope that most of our confusions would be resolved. But I also know that few will remain. Okay. कुछ कुछ और बनती जाएंगी आपकी कंफ्यूजन्स. ऐसा नहीं है. When you go deeper and deeper into random processes, few of your concepts are clarified, but more and more doubts emerge. Okay, और doubts बढ़ते जाएंगे. So then you have to dig deeper. But one day you definitely overcome all these doubts. But one day, it means you cannot just study in 2 days and you are done. Okay, it takes some time to understand this. But for the purpose of our study, I hope whatever I am doing today, or maybe in 1 or 2 more lectures, that would suffice. But still, if you have doubts about the theory, we can discuss them offline. You are welcome. Okay. So when we observe the voltage waveform, voltage waveform generated by the noise source, we see one of the sample functions. Now, how do you obtain the sample functions? So this is important for me to write, although I have explained it above. But for those who would be reading things from notes, they must get it the place. Sample functions can be obtained by observing simultaneously the outputs of many identical noise sources. Okay, so I think this is pretty much clear in itself. So in our today's lecture, we would mostly be writing a lot of things on this notebook. But from next lecture onwards, we will be doing more mathematics for random processes, so that we define our white Gaussian noise process properly, which generally adds to our pulse transmission, and we study our receiver design subsequently. Okay, so to obtain all of the sample functions, in general, an infinite number of noise sources would be required, that you can clearly see would be required. See, I am not going into the depth of this sample space and events in sample space. If at all you do not remember it at all, it means you don't know. So I would suggest, before reading random processes from some textbook or from the notes, please go through this from Ross's book, or you can refer to the lecture notes of the probability course, which you have already done. This will allow you to basically study whatever is written in the textbooks well, because textbooks will assume that there is a definite sample space, and on that sample space they will build this random processes. Okay, so this is important. And then how do you create events? So you have a sample space, and when you take possible collection of the elements of sample space, you generate events, and on that events you can define random variables and random processes. Okay, so random variable maps those events into constants. Constants means it takes a value. It will say that this event, it associates a constant value with an event. But random process, what it will do it, that for with an event it will associate a waveform. It means time comes into the role. Okay. So we have written earlier, I think, let me check if you have written that random process is an index set of random variables. Yeah, we have written index set of real functions. So let me be more specific now. So our random process, we have written earlier, but I am writing it for the sake of completion right now. A random process may be described by an indexed set of random variables. Okay, like define a set of random variables v1 is equal to vt1, v2 is equal to vt2, and subsequently this goes on, where vt is the random process. Okay, so what we are doing is that, let us say, given a random process v of t, you are saying that let me collect the several possible random variables by which you fix t. So for t1, I think we have shown it in the figure that you fix t1. So at the same time I am observing this random process, let us say daily I am observing at the same time 9 a.m. So I will see different possible values. So I will say that at T1 this is one random variable. Okay. Similarly at T2 this is another random variable. So this is the way we can extract random variables from the random process, or you can observe random variables from a random process. So just fix time T. So at the particular time, random process is nothing but a random variable. Okay, and this random variable would be built over the same sample space to which E belongs. Okay, so we have events E. As we move ahead, this would be more clear. Okay, here the random variable Vj, the random variable V of j, which is defined as V of Tj. Yes, somebody unmuted. No one. Okay. No, if you have to say something, you can. Here is a random variable Vj, which takes on the values, described by the set of constants P of and comma E of I for all I. So this is what I think you can read. So the random variable, how we had extracted, we said that we will fix the time. So we have fixed a time that is T of j. So at T of j, we say that the random variable is V of j. Now, what are the possible values which V of j can take? That will be described by you fix time and you vary E now. Okay, that is what is being done here. That let us say at a particular value T1, for E1 the value is this, for E2 the value is this, for E3 the value is this, and for E4 the value is this. And this E, that is the sample space to which E belongs, so that how many elements are there, so that depends on that. So you collect all those values. So the random variable can take values from this set. Takes on the values described by the set of constants. This. Now you will say that when we know that this is a fixed set to which Vj belongs, but you cannot say what value it takes because it depends on this number E of I, and I is varying, and this E of I itself is random. Okay, so once this E of I is random, so you will get random values for a particular time. So somebody has unmuted. So do you want to say something? Yes. Okay, this is Meet. You want to say something? I think this is Meet Rathod should be. Yeah. You are not audible. If you are saying something, at least you are not audible to me. You can type. So basically, you can type in the chat window. I will just read and then respond. Basically depends upon. Basically depends upon probability over. Okay, so this should be clear because E itself is a random, you can say a variable or event. So obviously the value which V of Tj will take will depend on the probability over space to which E belongs. Okay. In order to build some base, we need this. Okay. Otherwise, we would be just saying that white Gaussian noise is a random process, and you don't know what random process is. So we are doing in a very crux manner for our understanding as well as for our general knowledge. Okay, it should be there that we know what really a random process is. It should not be that we just comment that AWGN is a random process. So that is why you should do it, you should study it, you have sufficient background of probability built through several other courses. So it is in your good spirit to do it. Okay, you should do it. So for example, let us take an example. So for example, suppose that the noise source has a Gaussian distribution. Okay. Then any of the random variables will be described by f of Vj, V of j is equal to 1 upon root 2 pi sigma j square, sorry, it should be sigma j, e raised to power minus of V of j minus m of j square divided 2 sigma j square. Okay. Where V of j is multiplied by V of tj. So let us say if you say that you have a Gaussian random process, so for each of the time it is a Gaussian random variable. Okay, that is what the meaning is. V of j means the value that the process takes at time tj, and the distribution would be a Gaussian distribution. Okay. So जो हमारा white Gaussian noise है या Gaussian noise है जो हमारे सिस्टम में है वो इसी टाइप का एक रैंडम प्रोसेस है. बेसिकली इट इज अ Gaussian random process. Every time it takes a value which is a Gaussian random variable. Okay. So PDF okay, depends implicitly on time. So up to now we have not defined that. We know that for a random variable we can say that this is the PDF of the random variable. But for the random process, now what is the definition of PDF? Now PDF becomes a function of time. Why? Because we say that for a particular time t of j, we get a random variable v of j. So if at all I say that this has a PDF which is PDF j, so it means that for a random process at each time tj I will get a different PDF. I can get a different PDF. So PDF is a function of time now. Okay. So PDF depends implicitly on time. PDF depends implicitly on time. Okay. Since, so if in the current example, since m of j and sigma j respectively correspond to the mean value, and standard deviation. This is important to understand. Standard deviation measured at the time tj, measured at the time t equal to tj. Okay, this should be clear. Let us see this figure. From the figure we can see this. So let us say if you fix a time t of 1. So at t of 1, I am evaluating the mean. Okay, and at t of 1, I am evaluating the variance. Now this mean and variance can be strictly different from whatever the mean and variance I will observe at t2. So it means at t1, I get a Gaussian random variable with a particular mean and variance, but at t2, I will again get a Gaussian random variable, but the mean and variance can be different. Okay. So the PDF implicitly then becomes a function of time in our current case. And in general case also, because at t of j we are getting one random variable, basically this random variable depends upon time, so the PDF also depends upon time. Okay. So now to describe a general random process, x of t completely an n-dimensional PDF, an n-dimensional PDF, we will see f of x, x of bar is required. Okay, where what is x bar? Let us write it down. X bar is x1, x2, x of n. X of n, where x of j is denoted by x of tj. Okay, and n tends to infinity. So this is important. So I will give you 1 minute to read it. So when we say that at each of the time we have random variables, okay, like this, let me be more specific. Suppose on this axis I am sampling time. So t1, t2, t3, t4, t5. So 5 time instants. At each time instant I have a random variable. This is v1, this is v2, this is v3, this is v4, and this is v5. Okay. Now, in order to basically write the PDF of this random process, suppose this is my random process v of t. So, in order to write the PDF, what I have to do is I have to find the joint PDF of all the random variables. So, in terms of the joint PDF, I can write the PDF of VT. So, VT is nothing but the VT follows a PDF which is given by this. Okay. But this is a joint PDF. So, joint PDF then specifies the PDF of V of t. Now, this was an example to understand, but in a general random process, if this t is a continuous random variable, then the way to define it is that you take an n-dimensional vector and you tend n to infinity. It is simple. So, this is the way you can describe a random process completely. Okay, I think this should be clear. Okay. So, furthermore, the n-dimensional PDF, is an implicit function. Of n time constants. T1, T2, T of n. Since f of x, x bar is f of x okay. This should be clear because we have taken these random variables at particular times. Okay. So this becomes the TDF becomes a function of particular times. With respect to this definition, we have not yet said that t is continuous random variables. How do you really define? Or sorry, t is continuous. Then how do you really define this joint PDF? We are assuming that even if the time is continuous, we are taking n values and we are tending n to infinity. Okay. But even if we do that, we do not exploit this t axis fully. Okay. We have a lot of points in between. Hence, this becomes a function of those points we are taking t1, t2, t3, tn. Even if n is tending to infinity, this capital N number of points का ये implicit function होगा, because we have seen that at t1 there can be a different mean and variance, at t2 there can be a different mean and variance. So suppose this PDF comes out to be in terms of mean and variances of these capital and random variables, so it implicitly is a function of the time at which these are calculated. Okay, so now we have two bifurcation, but is a continuous random process or discrete random process. Okay, so continuous, this is not continuous time, continuous random process, not continuous time random process. This should be remembered. This is continuous random process. Okay. So you have in this continuously distributed random variables. Basically those who have PDFs, okay? Distributed random variables. V of j equal to V of t of j. Example, Gaussian random process. This means that, let us say the sample random variables have a continuous distribution. Meaning is this. If they have a continuous distribution, it means they will be characterized by PDFs. And the second is discrete random process. Okay, the discrete random process, obviously, it will lead to random variables with discrete distributions. Okay. Random variables with discrete distributions, and they can be well characterized by PMFs, that is probability mass functions. Okay. I would write in bracket PMFs, and this should be PDFs, so that there is some brushing of the concepts from probability theory. Okay. So we have an example. We can see it from the textbook of this discrete type of a random process. So the example is, this is the example. So you will have finite levels. Okay, time here is continuous, but the values which x of t takes is finite. You can take values in, it is finite. Okay. 1, 0, 1, 1 minus 1, 1 minus 1. So you have several possible waveforms. Here it is sort of a continuous thing. Okay. The value at t1 belongs to a much larger set, and the value at a particular time for the discrete random process belongs to a finite set. Okay, finite incountable. So I want to do one example before I close the class for today. Okay, so that example I hope should give you a feeling. Okay, so let x of t is equal to, suppose let us take a simple function, a times sine of omega naught t plus theta. Okay, so let us see that how really random process arises. Okay, be a random process. Okay, so this is a random process. Now, how it becomes a random process, let me tell you. So where a and omega naught, with a and omega naught are deterministic constants. And theta naught is a random variable. Okay. Now you can see, if you since theta naught is a random variable, whatever value theta naught takes, you will get different time waveforms. Okay. Here the time waveform for particular time waveform will be deterministic because of this sine function, but it will create an ensemble of waveforms because theta naught is a random variable. Okay, and theta naught is a random variable. T is the time parameter. Okay, T is the time parameter. Now let us put a distribution on theta. So let theta naught is uniformly distributed over minus pi to pi. Okay. Then let us define a zeta, which is equal to omega naught t plus theta naught, is a random variable for a particular t, obviously, is a random variable uniformly distributed over the interval. This is quite easy to derive. Omega naught t minus pi to omega naught t plus pi. Suppose I assume that this can take a value minus pi and plus pi with equality. So you will get that zeta will be distributed over this uniformly. Okay, because omega naught t for a particular t anyways is a constant, or for all t it becomes a constant. Theta naught is a random variable, so this will, because of the addition of a constant to a random variable, you can say that this random variable will also have the same distribution, but the parameters may be somewhat different. Mean will be different. But it will be uniformly distributed, and we can calculate the range easily because theta naught lies from minus pi to pi. So you just add omega naught t to it, so you will get the range. Okay. So the PDF for x of t for a fixed t, if you like, for fixed t is, so I am not evaluating it. This is a homework that if at all there is an addition of how will you calculate the PDF of x of t. Okay. This can be easily done from the concepts you have built in probability theory. So this is 1 upon pi times root of a square minus x square. Okay. Is then equal to a. Okay, and 0 for x elsewhere. So this derivation is a homework. This derivation is a. Okay. So what do we observe? Let us write it down. So the inference is that this random process. So what is the inference? Inference is that this PDF is not a function of time. Okay, time t. This is very interesting to see. Okay, and this lands up to the class of what we call stationary random processes, and they are very important class of random processes because our Gaussian noise, it will be assuming adds to our system, will belong to this category of stationary random process. So we have just introduced the concept, at least, or we have just, you can say, get a feel of the concept from this example. So this example says that even if I am evaluating the PDF for xt for a fixed t, I am saying I am fixed in t. So t should be there inside, no? F of x may t aana chahiye. But you observe that there is no t. It means whatever t I fix, if I fix it at t1, I fix it at t2, I fix it any value, I will get the same PDF. So it means that the PDF is not a function of time now. And this is what is the class of stationary random processes. Okay. So I think that we are done for today, and we would start from stationary processes in the next lecture. Okay. So if you have any doubt or anything to say, you are most welcome. I am there online for another 5-7 minutes. Others can leave.